Good morning. I'm going to talk about the Planck length. This is a repeat. I derived it quite nicely before and I posted it. I'm going to repost this as a replacement video. It will look just the same, except for one thing. In the previous video I had a really stupid typo on the very important number Planck's constant, which everybody knows. I just don't want to have that on the web. Other than that, everything is the same. This time I'll do things in reverse. I'll write down what the Planck length is in terms of the three fundamental constants, and then I'll work back and talk about it, but I will derive it from first principles and show you how to get that. Now, from the Planck length we can also get the Planck time, and by the same method we can get the Planck mass. But I will also refer to other natural units, Stoney units, due to George Stoney. Here are the people involved. We have Max Planck, who lived between 1858 and 1947. Einstein spoke at his funeral. Einstein was very admirative and proud of him. He liked him. The other guy is George Stoney, Irish, man before his time. He came up with Stoney units, and I recommend you go away and look at my derivation of the fine structure constant. It's there on the web. A lot of people don't care about this stuff. You don't get asked this stuff in college or in school, and it's the great stuff in physics, you know. And small. I kept mathematics to a minimum. You don't need calculus for any of this. So this time we're talking about the Planck length, and I will derive it, and this is what it looks like. Okay, it's a small length. It's a length at which a lot of people who are string theorists think that string theory comes into play. It's definitely a length whereby the thermodynamics of a black hole becomes into play. The entropy of a black hole, for example, is found by deriving the Planck area, which is LP squared, into the area, the surface area of a black hole. This is very interesting. This is counting bits. I will come to this too, okay? So where do we get the Planck length? The Planck length comes from combining the three fundamental units of nature, and we don't know why they have those values, in such a way that you can get units of mass, length, and time. Planck realized this, I forget the year, let's say 1900 approximately. It's almost important as his Planck radiation formula. If you eliminate one of the constants of nature, the G or the H or the C, you won't be able to form units of mass, length, and time. Any one of them, take it out and it doesn't work. If you add in an extra unit, such as the permittivity of free space, it doesn't work. You don't get units. Now, very strangely, Stoney figured out that you could make units before Planck's constant was discovered. It was with the discovery of Planck's constant that these things happened. So let's write down our three constants first. Now I'm moving slowly because I'm recovering from a slight injury. Ouch. So, the universal constant of gravitation is called G, was measured by Cavendish. In exactly 1798. Once he measured that, then we could find the mass of the Earth. Now this is not the same as little g, which is 9.8 meters per second squared, the acceleration due to gravity on the surface of the Earth. Students confuse that. This is big G. The universal constant of gravitation is a measure of the force of gravity between 2 kilograms of mass separated by a distance of 1 meter. That's how strong the force of gravity is. 6.67 by 10 to the power of minus 11. You have a kilogram here and a kilogram here, and the distance between them is 1 meter. That's what the G is. Now c is the speed of light. We're sticking in SI units. The speed of light in SI units is 3 by 10 to the power of 8 meters per second, or 13 million meters per second. Okay. Now in miles per second, it's 186,000 miles per second. That means in 1 second you're at the moon. In 8 minutes you're at the sun. In 4 years you're at the nearest star, Alpha Centauri, and so on. It's the speed of light. Now h is a measure of the energy of a photon proportional to the frequency of the photon. The energy of a photon in joules is h, Planck's constant, times the frequency. Frequency is the number of vibrations per second that the light wave is making, the photon of light. Okay, that's Planck's radiation. That comes into Planck's radiation formula. Now h can be measured experimentally from the photoelectric effect experiment, for example. It's 6.626 by 10 to the power of minus 34 joules seconds. Now there is a reduced Planck's constant, which is appearing up here actually. Some people don't know whether you're supposed to use the Planck's constant or the reduced Planck's constant in the Planck length. It just varies the Planck length by an order of square root of 2 pi, okay? And we divide h by 2 pi, you get 1.054 by 10 to the power of minus 34 joules seconds. Now my voice sounds funny because I said I'm recovering from an injury. Now in these things, usually you see these constants written in terms of newtons. Why not write them in terms of base units? The base units in the SI system are kilograms, meters, and seconds. So, newtons are kilograms, meters over seconds squared. Substitute in for newtons. And we get the universal constant of gravitation in terms of base units. So it's going to be 1 over second squared, kilograms, because that's kilograms, and that's 1. And second squared, and meters cubed. Meters cubed upstairs. So these are the base units for the universal gravitation constant. Now for meters per second squared, it's already in base units. And we don't need this one. This version of it we don't need. Now for Planck's constant, joules seconds, we substitute in for joules. Joules are Newton meters, or kilograms, meters squared over second squared. So Planck's constant in base units are kilograms, meters squared over seconds. Why am I doing this? Because I use, when people do dimensional analysis, what we're doing here to derive the Planck length is applying dimensional analysis. We're writing up an equation and we're making sure that the combination of quantities on the right hand side is dimensionally equivalent to the combination of quantities on the left hand side. By example, you will see. So, let's look now at, okay, and these will be the same units. The same. Okay? And we've got that there. So I'm going to gather up what I know. The G, the H. Actually, I'm going to use h cross. And the C. So we don't need to carry this burden of figures and symbols anymore. Now let's just make sure that I got those things correct. Okay. Now usually when you see people doing dimensional analysis, people do this. They put them in little squares and they play around with exponents up here. Symbol for length as a dimension, mass as a dimension, and time as a dimension. I'm just using the symbols, the kilogram, the meter, and the second, the SI symbol, to carry through with our calculation. So here we go, find the Planck length. So I want to find LP. So we're going to make sure that we have some combination of G, H, and C, which will multiply together, give dimensions on the is my right? Yeah, my right hand side of length. No seconds and no mass dimensions, just meters. We want to find out what G, A, B, and C is. Is A 6? Is B 10? Is C whatever? Okay, so to do that we'll incorporate our dimensions first and we put in the numbers later. Now that will give us three equations. One which the right hand side will be equal to 1, another one with the right hand side equal to 0, and another one with the right hand side. And let's see what they are. So let's deal with the meters first. The contribution for this term is meters to the power of 3a. The contribution here is meters to the power of 2b. And here, meters to the power of c is meters to the power of 1. So that's meters to the power of 3a plus 2b plus c equals 1. Okay, so we have the first equation. By equating the exponents, 3a plus 2b plus c equals 1. Next we look at the seconds, okay? This term here, well the seconds are downstairs, so this is going to be like a negative exponent if I brought it upstairs. Negative exponent upstairs, negative 2 times a, gives me the first part. This one here, negative 1 times b. And this one here, negative 1 times c. On the right hand side, we have seconds to the power of minus 0. So my negative 2a, negative b, negative c equals 0 is our next equation. And the third equation. For the third equation, we look at the kilograms. And I'll just zap through this one because you see the pattern now. So I get kilograms to the power of minus a. Kilograms to the power of minus a. Kilograms to the power of 2b equals kilograms to the power of 0. Now all we have to do is solve these three equations simultaneously. I don't need this stuff anymore, so I'll do it over here. Now the birth, let's see. And what did I do wrong here? So for the kilograms part, let's check that again. Kilograms to the power of, I made a mistake here. This is only the power of 1. Sorry. Kilograms to the power of b. So the very first thing we've got is that a equals b. So a equals b. Let's come to this equation here. 2 3 implies, that symbol means that implies, 2 gives us negative 2a. Now a is equal to b. So we have negative 3a equals c. Okay? A is negative c over 3, whatever way you want to look at it. Now we go to the first equation. Equation number 1 is down here. So we leave it in A. So 3a. Now B, that's going to be 2a. And c is where? C is negative 3a. So this cancels, and we get a equals a half. Okay? 2a equals 1, so a equals half. Now a equals b, so b is also a half. Okay? And what is c? C is negative 3a, but a or b is a half. Wait now. A equals plus a half here, sorry. Okay, so a and b are a half. So c is negative 3 over a. So now I've got the three results. C is negative 3 over 2. Okay? Now we have our answer. So we have g to the power of a, h to the power of b, c to the power of c. That implies that g to the power of a half times h to the power of a half times c to the power of minus 3 over 2 is m to the power of 1, or the Planck length. Well, that's the same as writing g to the power of a half, h to the power of a half, c cubed to the power of a half, because the negative exponent means it's downstairs. Anything to the power of a half is square rooted. So we're square rooting this, this, and this. And we get the Planck length, an expression for the Planck length. And we put in all the numbers, the number for the number for g, the number for h cross, and the speed of light, all to be cubed, all square rooted. We put in all the numbers, deal with the numbers separately. Okay, c cubed. So there are the numbers, and now the powers. And this is to the power of a half. Now, 10 to the power of 10 cubed, 10 to the power of minus 24. And the answer is going to be in meters. Of course, this is all to the power of a half. Let's see. So we have that object here. Now it's going to be the same as this. Now I've got a minus 69 here, so in order to operate with this properly, I change the numbers. I make this 10 to the power of minus 70, so I've made the whole expression 10 times too small. I have to make it 10 times too big. throw the numbers in your calculator, you can kind of see that it's going to be 1.6 approximately. And negative 70 over 2, take the square root is negative 35 meters, and I get the Planck length. Given by root GH cross over C cubed. I have more to do with that. I've got to get to the Stoney units. I'll do that in the next part. I've actually done it before too though.